Hello guys, up till now we have studied the three types of negative feedback topologies analysis, and now we are ending up with the last analysis of negative feedback topology, and that is nothing but current shunt negative feedback topology. Here we have to discuss what will be the gain, input impedance and output impedance with feedback and without feedback. Let's start with this analysis. As far as current shunt the name is considered, current is the part of sampling, shunt is the circuit which is connected at the input side for the mixing. Okay, so we will write quickly what will be the parameter at the mixing, parameter at the sampling, and circuit at the mixing, circuit at the sampling. So for the sampling, the parameter is current. So whenever we use the parameter as current for the sampling, we generally with series combination. Okay, whenever we are using mixing and it is been given that it's nothing but the shunt mixing. Okay, so whenever we are using shunt mixing, we are also using here current. So it's a simple thing that current are there as a parameter for both input as well as output. So which amplifier we have to use? Yes, we have to use current amplifier, right? So quickly pause your screen and try to draw the entire circuit for current shunt negative feedback amplifier, and again come to me to tally it. This is the particular circuit that we are going to use for the analysis purpose. Let's start with the analysis. This is nothing but the input current without feedback, that is nothing but II. Input current with feedback, that is nothing but IS. This is nothing but the feedback that we'll be getting as IF. Okay, and now we will be in the position to write this particular value of the dependent current source, as we know that this is of the type current and this is also of the type current. I will be getting the current gain, that is nothing but AI multiplied by II, and that is nothing but the value for your dependent current source. So, and this black dotted line represents, it's nothing but your current amplifier. Okay, so as far as this circuit diagram is considered, we have noted, we did note each and every parameter for the current shunt negative feedback amplifier. Now let's start with the analysis. Before starting this analysis, we note that what will be your open loop gain. Okay, so your open loop gain is nothing but AI, that is in the form of current gain. So it's nothing but IO divided by II, right? And that is also called as gain without feedback. Okay, so far so well. Now we'll start with our analysis to find out the first parameter, that is nothing but the gain. Okay, so first parameter that will say, it's nothing but the gain with feedback. Gain with feedback, we'll have to start up with the KCL. We'll apply KCL at input. Where we'll have to apply the KCL? We'll have to apply the KCL at this particular part. We'll say that it's nothing but node number A. Okay, current flowing through this is nothing but IF. Total current is II, and the another current in another branch of RI is nothing but II. So I can say KCL at input node A, right? IS is equal to IF plus II, right? But what's the value of IF? value of IF is nothing but B into IO, and value of II is nothing but the value of current IO divided by AI, as the value of RO is much higher as compared to the RL. So more current, maximum amount of current, or rather all amount of current, all current will move from the resistance RL branch, and RO will be nearly equal to having less current, right? High resistance, less current. So I can say IF is equal to B into IO, and II is equal to IO divided by AI, right? What we will do, we will just put these values, IF over here and II over here. We will be getting gain with feedback, right? See, I will be having IS as it is. IF पे मैंने क्या किया, I'll put the value B into IO plus II के लिए IO divided by AI. So everything is in the form of IO and IS, right? So here we will be getting IS is equal to IO, I will take it common, and we'll be getting 1 plus AI into B divided by AI, right? Got it? So we'll say that gain with feedback, we will first define that. What will be gain with feedback? IO divided by IS. Instead of I will apply the IS as your input source, because if feedback is present, IF will come into picture, and IF plus II is nothing but IS. So IO divided by IS is nothing but your AIF, that is nothing but your gain with feedback. So what ratio I will be getting from this particular formula, that will come out to be AIF, that is equal to IO divided by IS is equal to open loop gain divided by 1 plus factor of open loop gain multiplied by B, that is feedback gain. Okay, and that is nothing but our first formula we are expecting from this particular feedback topology is gain with feedback. Okay, let's move towards the second part of this analysis quickly. That is nothing but your input impedance with feedback. Okay, input impedance with feedback is considered as RIF, and that RIF is nothing but VI divided by IS, right? So VI divided by IS मुझे find out करना है. Before that, I should have to know that input impedance without feedback. So if I'm not considering feedback, then IF will not be present as a feedback parameter. So IS will act as II only. So instead of IS, I will write it as II only. So without feedback, I will treat it as RI only, and it is nothing but VI divided by II. So instead of I will be writing it as IS to find out the input impedance with feedback. Okay, so let's try to analyze this with these two particular formulas, and with the same application of KCL. Apply KCL at node A at input. Okay, we'll say IS is equal to IF plus II. Yeah, I know that. What's the value of IF? IF is nothing but B into IO. So we'll write it as B into IO plus II. Okay. Similarly, I know that what's the value of IO? IO is nothing but A into II, AI into II. So here we will write AI into II into B plus II. So for this particular case, we will take the reason as IF is equal to B into IO, and for here we'll take the reason as IO is equal to AI into II. Okay, so ultimately, so we have got IS is equal to II into 1 plus AI into B, right? And now from these particular equation, we will write it as Is is equal to Vi divided by Rif and Ii is equal to Vi divided by Ri. Simple. So we will say that what is Is? Is is nothing but Vi divided by Rif and Ii is nothing but Vi divided by Ri, and here we will be getting the same factor 1 plus Ai into B. From here we will get to know that Vi ni Vi ko maar diya, I will be getting that Rif is equal to Ri divided by 1 plus Ai into B. So here my input impedance is decreases if I apply the feedback. This is the second formula that we have got as your input impedance with feedback. Okay, let's start with the analysis of output impedance with feedback. So the third part is output impedance with feedback. Now for that, note that here, see to it that as far as this current shunt negative feedback amplifier is considered, I know that at the output side I have to have the voltage source, which is nothing but the supply, and at the input side I want to have the current source, which should be replaced by their respective internal resistance. As the current source is having internal resistance as infinite, then I will open this current source. So what I have to do? Connect. I'll have to write connect external supply Vx at output and open the input supply Is, that is 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 equal to 0, right? Now we will form the complete circuit as with this particular configuration. We will make sure that here we will say it is nothing but the current source, and that is nothing but Ai into Ii. This is nothing but the resistance parallel along with this. This is nothing but the value Ro having high resistance, and here we have to connect the value of voltage source Vx. Okay, so if we connect this value Vx, and obviously we don't bother about the load resistance, rather load resistance we open it, right? And then we will say, as far as this complete circuit is considered, this is nothing but the Ix. Okay, this is nothing but the IO. Okay, the current flowing through this particular RO is, let's say, and current flowing here is your AI into II. Okay, this is the value of current I, this is the Ix, this is the exactly opposite to the Ix, that is nothing but my IO. So if I apply the KCL at the node A, right, left part is this, such that I'm saying the current Is 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 open circuited, right? As it is written over here, Is is open circuited, replaced with their internal resistance. Rs is there. I can say that whatever this is nothing but your transconductance current amplifier, not transconductance, it's a current amplifier, and we can say this is connected over here, and the another part is at the load that we have nothing to do with this particular load part. Okay, right? So actually we opened that particular load part and we are attaching that power supply Vx. Okay, so concentrate on this particular part. We will say concentrate on this particular part. We will say that apply KCL at this particular node. We will elaborate that particular equation. Apply KCL at output node A. If we apply output node A by KCL, that is AI into II, that is incoming current, then two outgoing currents I will be having. This is equal to Vx divided by RO, that is nothing but the current flowing through RO, right? Current flowing through RO is nothing but Vx divided by RO, and plus I can say Ix. Okay, now I know that the value of Vx divided by IO is nothing but the value which we are expecting as your output resistance. Okay, fine. So far so well. We will say that what will be the value of the II if we are considering the Is is equal to 0. So here we will say as Is is equal to 0, II is equal to minus of If, right? As it is minus of If, we will say If is equal to B into IO, right? What is the value of IO, right? So IO is nothing but we'll keep this IO as it is, and then we will put this value in here, right? Then we'll try to get that what that equation will be, right? AI into, we'll take minus sign, B into IO is equal to Vx plus Ix. Okay, as far as this Ix is considered, we will say this AI, B, IO will keep this on right hand side. We will take this Vx on the left hand side. So minus of Vx is equal to Ix, right, minus AI into B into IO. Okay, as far as IO is considered, we know that this IO is minus of Ix. See this particular circuit, IO and Ix have different direction. As Ix is minus of IO, we can say that minus of Vx is equal to minus of IO in bracket 1 plus AI into B, right? Minus minus will get cancelled, and this is what we are expecting, Vx upon IO, which is nothing but ROF, which is nothing but here one thing is left, and that is nothing but Vx upon RO. Here it is Vx upon RO. छोटी छोटी मगर मोटी बातें, RO 1 plus AI into B. Okay, so it's a very simple thing that we have got. As here as well it is RO, it's a simple mathematical thing that was left, and here I can say that ROF that we have obtained in the form of the output impedance without feedback. So if we say we are applying feedback, your output impedance will increase. So this will become your output impedance with feedback. Okay, so far so well. Now we will conclude our session for the current shunt negative feedback analysis. These are nothing but the parameters. This is without feedback and this is with feedback. Okay, first part is gain, so we'll write it as gain is nothing but the current gain. So here we will say AI. Okay, AI is nothing but I'll not write it over here. It's AI. AI is nothing but without feedback, and it is IO divided by II. In here, we'll be getting AI. F is equal to IO divided by IS. It forms AI divided by 1 plus AI into B. Okay. Second thing that we'll be getting as input impedance. Input impedance is your Ri, which is nothing but Vi divided by Ii, but input impedance with feedback becomes Rif as Vi divided by Is, and that is nothing but Ri divided by 1 plus Ai into B. Okay. Third thing that we have got as output impedance. Output impedance, that is Ro, is nothing but Vo divided by Io, and here we will be getting Rof as with feedback. What is it's with feedback? With feedback is Ro multiplied by 1 plus Ai into B. Simple. So this is how we have got the complete conclusion for voltage shunt negative feedback. Conclusion is left that when we are applying feedback, your gain decreases, your input impedance also decreases, but your output impedance increases. So few parameters are decreases, few parameters are increases, and that we have concluded with a conclusion of current shunt negative feedback analysis. So we have completed all the feedback topology analysis, and in the next videos we will learn the problem based on the negative feedback amplifier. So stay tuned for that. Learn more and more EDC along with me, along with Ekeeda videos. Subscribe this channel of Ekeeda videos. Thank you so much.